So what does it mean to solve a differential equation? Well, you've been doing this since C1. Solving a differential equation means finding the y that satisfies the equation. So in this case, we want to find a y. We don't know what it is. And we want the y to be such that if we differentiate it and get dy by dx, and then we take away 3x squared, then what we'll end up with is 2. Let's move the 3x squared to the other side. Dy by dx equals 2 plus 3x squared. Now if we know what dy by dx is, we can integrate both sides of this equation. The integral of that side dx equals the integral of that side dx, and we get y equals 2x plus x cubed plus c. And we're done. We've found the solution to the equation. Now what if I come to you and I say, I've solved this equation actually. I've found the answer. It is 2x plus x cubed. That's the answer. I can prove it. If you take y to be 2x plus x cubed, then dy by dx is 2 plus 3x squared. So then if you stick that into the equation, dy by dx minus 3x squared is just going to equal 2, and that's what you wanted. So good, I've done it. Brilliant. What would you say to that person? Well, you would say, you forgot plus c. And they would say, so? I solved the equation, didn't I? You asked me to find a y so that dy by dx minus 3x squared is 2, and I did. There's the y. dy by dx minus 3x squared is 2. Brilliant. What's the use of that? And the point is that a general solution to a differential equation, there's infinitely many of them. Infinitely many. And what we found here in the 2x plus x cubed, that's called a particular integral. It does solve the equation. No one can argue with it. 2x plus x cubed does solve this equation, but it's not the end of the story, because there is also this plus c. C for complementary. It's complementary solution on the end. Now the complementary solution, when we differentiate, disappears and it doesn't contribute anything, so it's invisible really. Once you start to do the nuts and bolts of the equation, it disappears, but we need it in our general solution because that gives us a full family, infinitely many solutions, a family of infinitely many solutions to an equation, not just one solution. And when we solve our second order differential equations, we're going to be looking for both these parts of the solution. A particular integral, which solves the equation, and a complementary solution, which kind of disappears once we start using it, but provides us with a family altogether of infinitely many solutions to the differential equation, not just one. So this example obviously looks a lot harder. It's a second order differential equation, and the general solution that we're looking for is going to have two parts to it. It's going to have the complementary function and the particular integral as well. Now the particular integral is the thing that basically solves it. It's the thing that if I find it and I differentiate again, and then I get these three terms, and I do the last one plus 7 of the second one, and then I add on 12 of the original thing, then I will indeed get 28x plus 5. But we're also going to get this complementary function, which will be the equivalent of the plus c in the sort of differential equations you've seen in the first year of your A level, and that's the bit that's going to basically disappear, and it's just going to provide a load of bulk. It's going to provide us with infinitely many solutions instead of just the one. So let's see how it works. Normally we start by finding the complementary function, but for the purposes of this example I'm going to start by finding the particular integral. I'm going to start just by trying something completely random and see what happens. I'm going to try y equals x squared plus 3. And I'm going to differentiate it. Just, you never know. Might have got lucky. This might be the answer. D squared y by dx squared equals 2. So let's put these into the equation and see if I got lucky, and it's going to produce 28x plus 5. So second derivative, add 7, lots of the first derivative, add 12, lots of the original function, fingers crossed, equals 2 plus 14x plus 12x squared plus 36. I don't think this is going to be good, is it? Okay, plus 14x plus 38. Okay, that didn't work. That is not 28x plus 5. Okay, well, it was a long shot. We can try something else. Now, before we try something else, let's have a think about why this didn't work. The main reason that this didn't work is that I've ended up with an x squared here, and what I was hoping to get is 28x plus 5. There's no way having an x squared, no matter how many of them, no matter even if this came out as 28x plus 5, that's causing a major problem. So where did that come from? Well, the 12x squared came from here, because I introduced it as part of my y. So regardless of what else I had, if I've got an x squared in here, well, differentiating it's going to make it turn into an amount of x's, and then it will be an amount of numbers. So it's not going to cancel with anything. So putting it in with the y means it will be in that final answer when I expand it all out, which means I will be sad because I wanted 28x plus 5. I didn't want any x squareds. So this gives me an idea of where to start for the next guess. Okay, guess number 2 is going to be a bit more intelligent. Look at the right hand side, 28x plus 5. What form is it? What shape is it? What type of thing is it? Well, it's linear, ax plus b. So what I'm going to do is I'm going to start by guessing something linear. I don't know, 4x plus 7. Okay, let's try that. Slightly more intelligent guess than just randomly going for a quadratic. So d squared y by dx squared would equal 0. Let's put all of those into the equation and hope for the best. So we've got 0, add 7 lots of 4. Oh, that's 28. Oh no, I wanted 28x. Okay, it might still happen, it's okay. 4x plus 7, so we get 28 plus 48. Oh, that's the wrong amount of x. Plus 7 times 12. Yeah, this is not good, is it? Okay, well it's better though, because at least I've got some x's and some numbers. What have I got? 112 there. So at least I've got the right shape. So this idea of looking at the shape of the right hand side and starting off with that shape, that was a good plan. It's just that the 48's wrong and the 112's wrong. So I know, because I want ax plus b to pop out on the right hand side, I know my particular integral is going to be in the form y equals ax plus b. I just don't know what a and b are. So let's force a and b to be correct. Let's differentiate again, and then put all of these into the equation. So we get the second derivative plus 7, lots of the first derivative, plus 12, lots of the original function, and I'm going to force this to equal 28x plus 5 by comparing the coefficients. How many x's are there and how many numbers are there? And then compare that with the 28x plus 5 and just choose a and b to make it work. So 12a, that's the amount of x, that needs to equal 28. So that gives me a is 7 over 3. Okay, numbers. 7a plus 12b has to equal 5. And I know what a is. It's 7 over 3 plus 12b equals 5. And if you rearrange that, you get b is minus 17 over 18. Woohoo, we found our particular integral. Our particular integral is going to be the thing that's going to work, and I will check it in a minute, but pretty confident, is going to be 7 over 3x minus 17 over 18. Now that was a far more intelligent way of finding it than just guessing loads of different things and hoping to hit upon it. Let's just check it does work. Okay, so dy by dx, if y is 7 over 3x minus 17 over 18 is 7 over 3, and d squared y by dx squared equals 0. If we put all these into the equation, we get the second derivative plus 7 lots of the first derivative plus 12 lots of the original function minus 17 over 18, and if you simplify that and tidy it all up, 49 over 3 plus 28x plus 34 over 3, which is 28x plus 5. Brilliant. We found it. So we found our particular integral. Now don't forget our general solution is made up of two parts. It's made up of the particular integral, which we found, but there's also a complementary function, which is going to be the equivalent of the plus c. It's not going to contribute anything, but it's going to all disappear when we actually go through the process of differentiating, but it's going to allow us to create a family of infinitely many solutions to this equation, not just the one, which is 7 over 3x minus 17 over 18. Now the complementary solution, the complementary function, is something that doesn't really contribute anything on this left-hand side. So when we put it in here, it all basically disappears. It's just disappeared. Just like with dy by dx, if you have c, when you differentiate you get 0, so it just disappears. So we're looking for a function which, if we multiply it by 12, add on 7 of its derivative and then add on its second derivative, then everything just magically cancels out and it's just gone, invisible, gone. And then we're left with a particular integral which we know contributes to 28x plus 5. So what sort of function would do that? Well, it's not going to be a polynomial, a cubic, a quadratic, anything like that, because if you get that and then the highest power is 4, then here the highest power is 3 and 2, so your highest power of 4 has got nothing to cancel. So it needs to be something that doesn't really change when you differentiate it. Can't even be sine and cos, because if this was sine, this would be cos, this would be sine, so even if we could make these two cancel each other out by choosing clever amounts of sine, there'd be some cos here. And similarly, if this was cos, this would be sine, this would be cos. We could maybe get the coses to cancel, but there'd still be some sine left. So what we're looking for is something which is not going to change when we differentiate it, which, as you know, is e. So let's try e to the, well, I don't know, let's put m, e to the mx. Let's find m. What would m need to be to make this disappear when we stick it all in? Okay, well, we've got the first and second derivatives, they're pretty straightforward. E to the mx, we're going to take our ingredients, we're going to put it into that left-hand side, m squared e to the mx plus 7, m e to the mx plus 12 e to the mx, and we want this to equal 0. We want this function, this complementary function, to go into this left-hand side and then cancel itself out and produce 0. That's what we want. Okay, let's pull out the e to the mx. That leaves me with m squared plus 7m plus 12 equals 0. Okay, well that can't equal 0, so that leaves me with m squared plus 7m plus 12 equals 0, which gives me m minus 3, no, plus m plus 4 equals 0, which gives me m, oh, 2 m's, minus 3 and minus 4. Okay, so that tells me that if I have e to the minus 3x and e to the minus 4x, in fact I can have any amount I like of those, any amount I like, and when I differentiate and differentiate again, I've forced it to work that this will all produce 0, and that's my complementary function. Let's check it works. Well, the first derivative is going to be minus 3a e to the minus 3x minus 4b e to the minus 4x, and the second derivative is going to be 9a e to the minus 3x plus 16b e to the minus 4x. Let's put that into the equation. So we take the second derivative, 9a e to the minus 3x plus 16b e to the minus 4x. Then we add on 7 lots of the first derivative, minus 3a e to the minus 3x, minus 4b e to the minus 4x, plus 12 of the original function. And we're hoping that this is just going to produce 0. Everything is going to cancel itself out. So how many a's have I got? In fact, I can just divide through, oh no I can't. How many e to the 3x's, e to the minus 3x's have I got? I've got 9a, that's there. I've also got minus 21a, and I've also got 12a. And if you add them up, that's equal to 0. Good, that bit worked. What about e to the minus 4x? How many of them have I got? 16b, and I've got minus 28b, and I've got plus 12b. And again, if you add that up, brilliant, that equals 0. So it's worked, we found our complementary function. So let's have a look at our general solution. So here it is, our first ever solution to a second order differential equation. It's made up of 2 parts, a complementary function, which when you differentiate it again and do 12 of the first thing times 7 of the first derivative, then add on the second derivative, magically, by our clever choice of minus 3 and minus 4, it's all going to disappear. And we've also got our particular integral, which is the thing that's actually going to produce that 28x plus 5 when we put it in here. Now, as an exercise, what I'd like you to do is pause the video and work out what dy by dx is, and then work out what d squared y by dx squared is for this entire general solution, and then put it all into the equation d squared y by dx squared plus 7dy by dx plus 12y, and just check that you do indeed get 28x plus 5.